All right, Unit 2 marches on. Today, Lesson 6 deals with implicit differentiation, how to find the derivatives of functions defined implicitly. The derivatives of functions where we cannot get y by itself. Mr. Einstein helps us out with, well, that's inspirational, isn't it? So on today's show, implicit differentiation. This is one of the big consequences of the chain rule. If you don't regret the chain rule from yesterday's lesson, you will today. Let's quick talk implicit versus explicit. When we talk about explicit, if you were watching a movie and it had explicit sex in it, that would be right out there, no doubt about it. In a situation where a function is defined explicitly, you're looking at something like that, where y is all by itself, or it is possible to get y all by itself. In an explicit function, it is possible for y to be solved for on its own. In an implicit situation, if a movie had implicit sex, you would know that it's going on, you would know something's happening, but you wouldn't see it outright. In the same way, with implicit functions, an implicit function isn't always even a function, an equation where y is defined implicitly means that we have a situation like this, where it is impossible to solve for y all by itself. Even in a situation like this, it is impossible to solve for y by itself. We can get y equals plus or minus radical 1 minus x squared, but it's impossible to solve for y and get one equation. So these are situations where y is defined implicitly. It is not easy to get a hold of y. And so the thing is, equations like those are in many times smooth. And since they're smooth, we can find their derivatives. So since we can find their derivatives, we ought to be able to do that using some very easy process. And so I'm going to show you the process. Implicit differentiation takes 4 steps. First, we're going to differentiate both sides of the equation. With respect to x, we're going to use the chain rule. Then we're going to get all the dy dx terms to one side of the equation, all the non-dy dx terms to the other side. We're going to factor out a dy dx, and we're going to divide to get dy dx by itself. So 4 steps, and if you can follow those 4 steps, you win every time. They will always work. Differentiate with the chain rule, bring your dy dx's to one side, your non-dy try that again. Your non-dy dx's to the other, suck and divide. So let's take a look at that original equation, well, one of the original equations that we had up there. Find dy dx if x squared plus y squared is 1. If we're going to do this in an explicit way, we would have to say, okay, y is plus or minus the square root of 1 minus x squared. And we'd have to take the derivative of that. And I know from my chain rule that the derivative of y with respect to x, let's see, this is the square root of something. So that's 1/2 something to the negative 1/2 times the derivative of the inside. And so what is that? Well, the 2 and the 1/2 cancel, leaves you with an x up top, a radical on the bottom, and believe it or not, when you multiply plus or minus by minus, you get minus or plus. And so you have an ugly expression. It's explicit, but it's an ugly expression. If you choose to go implicitly, Then you follow my steps. And my steps say we're going to differentiate both sides with respect to x. So the derivative on the left side is 2x plus the derivative of y squared is 2y. But remember, y is not x. It's a function of x. So the chain rule says we have to multiply by its derivative. And I'll let that sink in for the folks at home. Y is not x, it's a function of x. So we have to multiply by its derivative. And of course, the derivative of 1 is 0. So step 2 says we collect the dy dx's all to one side. So we'll leave 2y dy dx on the left side and kick that 2x to the other side. We don't need to factor out a dy dx at all, and so we can skip right to step 4. We get negative x over y. So you give me any point on the unit circle. I can find the slope of the tangent line by taking the opposite of the x value and dividing by the y value. Now there's a whole bunch of you that are about to tell me, wait a minute, that is an unsatisfying result. And that is an unsatisfying result because it has a y in it. We're not allowed to have a y in it. Sure you are. I don't know who told you you weren't. You absolutely are allowed to have a y in your answer. The derivative of y with respect to x. Since we're dealing with a function that's implicit anyway, it's negative x over y. Okay. I'll do more. Find the slope of the tan to x squared plus y cubed minus 2y equals 3 at the point 2, 1. So if I'm going to find the slope of the tangent line, I want to find dy dx. To find dy dx, I've got to differentiate both sides with respect to x. The derivative of x squared is easy. The derivative of y cubed is easy. That's 3y squared. But remember, y is not x, it's a function of x. So we take the derivative of that, stick it on the end. Minus 2 dy dx's. Remember, y is not x, it's a function of x. So we stick its derivative at the end. And of course, the derivative of 3 is 0. So step 2 was we gather all the dy dx's to one side. So we're going to, really, 3y squared dy dx minus 2 dy dx equals negative 2x. Step 3 says we factor out a dy dx. You are already recognizing that some of these steps can be done in your head. And so dy dx is negative 2x over 3y squared minus 2. I want the slope of the tangent at 2, 1. So I evaluate this at 2, 1, and that gives me negative 4 over 3 minus 2. Negative 4. Every problem has the same rhythm. Every problem has the same rhythm. Time now for a quick who cares. Let's find the normal line to x squared y squared minus 2x equals 4 minus 4y at 2, negative 2. Time for a quick who cares. That function looks like this. And we're looking for the equation of the normal line. Now, everybody who's good at optics is going to tell you that that curved surface could be a lens, and we're looking to have light go through that lens. But we all know that light bends toward the normal, and so Since light bends toward the normal, you ought to know where that is, how it behaves. So finding the normal line matters. So we'll find the normal line. And we know what the equation of a normal line is. It's y minus y1 equals x minus x1 multiplied by the slope. So I need a slope, and to do that, I'm going to take the opposite reciprocal of the derivative of that. So product rule. First times derivative second, remembering chain rule. Chain rule. Plus second times derivative first. Minus 2, because the derivative of 2x is 2. Derivative of 4 is 0. Derivative of y is dy dx. Now, two options here. We could bring all the dy dx's over to one side, suck and divide, and that would be fine, except that we're not interested in what dy dx is in general. We're interested in what dy dx is there. And so it is perfectly conceivable for us to make substitutions now. X squared is 2 squared, that's 4. Y is negative 2. Y is negative 2. X is 2. And so we can get what dy dx is. That's negative 8 on this side. Kick it over to the other side. That'll give us 4 dy dx's equals 14. What's that? 14 over 8? 14 over 8. No, I'm totally wrong. Let's just do it. 4 times 2 times negative 2 is negative 6. That's the problem. Negative 16 dy dx's plus 16 minus 2 is negative 4 dy over dx. So bring the negative 16 over. And so dy dx is 7/6. It's 7/6. That's the slope of the tangent line. I need the slope of the normal line, so I take the negative reciprocal and I put a box around it. Every implicit differentiation problem has the same feel. You take a derivative using the chain rule on both sides, collect, factor, solve. I promise they all go this way. Okay, so we'll see you tomorrow with more practice. Till then,